Hey me, what are you doing? I'm calculating how many subframes I need for each of my filters using my SNR app to get a good image. It's kind of tedious because I can't see all of my filters at once. Oh, well, I've improved it. You can now put in values from different subframes and see the results all at once. Really? Yeah, let me show you. Welcome to Deep Sky Detail. Have you ever wondered how much integration time you need to get a good astronomy image? I have, and the answer really depends on a lot of things, like your telescope's aperture, the f ratio, the pixel size, the brightness of your target, light pollution, and the list goes on. There is no real one answer. You really need some sort of calculator that can help you quantify the quality of your subframes. It would need to be able to figure out how much light pollution is part of your signal, for example. Luckily, last year I implemented this into a web application that you can use, and now I've made it even better. A few years back, I read an article by Craig Stark on calculating signal-to-noise ratios. Craig Stark is the original developer of PhD, a neuroscientist, and pretty much my hero. The article is still up on cloudy nights. In it, he explains step-by-step how to measure the signal-to-noise ratio of part of an astro image. He even created an Excel spreadsheet to help with calculations. However, when I try clicking on the link to the spreadsheet, it no longer exists, and neither does his website, which is unfortunate because I really enjoyed reading his blogs. Signal-to-noise ratio, or SNR, is probably the most important concept for understanding how to get a good image in astrophotography. It's just the ratio of the light signal coming from the deep sky object to the noise. Noise is random variation caused by your camera, light pollution, and even the deep sky object itself. The higher the SNR, the better your image will look. But then I got a few questions from different people in my email about calculating integration time for monochrome cameras and other things. I've recently realized that I can make the app better simply by allowing people to put in multiple values for different types of exposures. Why would this be helpful? Besides just estimating things for different filters, one-shot color cameras can benefit as well. But before we get into that, let's see how the app works. Also stick around to find out how to use the app and where you can access it. I'll explain how to get the most out of the plots and troubleshooting when the app seems like it fails. So here's the app. I've removed all the default values for this demonstration. There's nothing useful right now. What we need to do is figure out a few values and put them in these boxes. The values can be put in any order, but until you've put all the values in, you'll get these error messages. Don't worry about them at this point. For this demonstration, I'm going to measure the SNR of Messier 42, the Orion Nebula, for 3 of my narrowband filters, 𝗳𝗿𝗃 and S2. The easiest thing for me to figure out right now is the exposure time in seconds. I chose that time before I started imaging. They're 5-minute exposures, so I'll input 300. 300 seconds is 5 minutes after all. Next, I'll need a couple values related to my dark signal and bias signal based on the gain that I took from my subframes. I know the rough numbers for the camera are 1966 and 1909. Fun fact, the value of the dark signal when properly calibrated out of your light frames doesn't really affect the SNR estimate. That doesn't mean you shouldn't take darks and use them, it just means that the dark signal cancels out itself when calculating the signal-to-noise ratio. So theoretically, the dark signal value in this app could be anything. But let me go ahead and double-check these numbers anyway. I've opened up a bias frame in Serial and I'm going to right-click and check the statistics. The median value is 1920, so that's what I'm going to use for this app. I'll do the same thing for my dark frames. I also need to know 2 more numbers: my camera's gain in electrons per ADU and read noise in electrons. If you have a dedicated astronomy camera, the manufacturer gives you these numbers. If you have a DSLR, it's a bit more complicated, and I made a video on how to calculate the gain and read noise for your camera. I'll put a card at the top of the video for DSL owners to check it out. So I use a 𝗳𝗿𝗹𝗹 Pro camera in bin 2x2 mode at Unity gain, or 120 gain. I'm on 𝗳𝗹𝗹's website to look up the numbers. As I scroll down, there are a few plots that are interesting. At gain 120, the gain in electrons per ADU is around 0.9 to 1. Go ahead and put 0.9 in this gain box right here. For read noise, it looks like at 120 gain, it's about 1.9 electrons. so I'll put that in the read noise box. We also want to specify our target signal to noise ratio in the desired SNR box. The rule is this: more SNR, more better. But that's sort of non-specific. So a better rule of thumb is probably you want an SNR of at least 30 for the midtones of the DSO. That means your signal is 30 times bigger than your noise. 30 is okay, especially for fainter parts of your target. 60 is good, and 90 is really pretty good. But note that SNR in this app is measured as raw SNR, so 90 SNR does not look twice as good as 45 SNR. In other words, the relationship between raw SNR and your perception of how good an image looks is not, at least to my knowledge, a one-to-one relationship. For example, 135 raw SNR might be twice as good as 45 SNR, and 810 SNR might be twice as good as 135. I'm just spitballing numbers here, so don't quote me on this. But basically, there are diminishing returns to going higher and higher with SNR. But I think that around 60 is a good starting point for HA, especially for the Orion Nebula because it's so bright. So now we need two more numbers. These are going to come from our light frames. We need the DSO plus SkyGlow signal and the SkyGlow signal. What happens behind the scenes is the app will subtract the SkyGlow signal from the DSO plus SkyGlow signal to get the signal for the DSO, which is what we need for the numerator of our SNR measurement. Because I'm going to put the results from my HA filter first, I'll put HA as the filter label, but you can label this as anything. For example, if you were doing a test between 120 second and 300 second exposures, you could label this as 120, 120S, 120 seconds, HA 120, or whatever you want. Just make sure you don't have a comma in the name. Why? You'll see in a minute. So let me open up a light frame in Serial to get the DSO plus SkyGlow signal. Make a selection of the target that you want to find the SNR of. Remember, you're only finding the SNR of the portion of the image that you select. Selecting a different part of the nebula or galaxy will tell you the SNR for that part of the image. Come to think about it, this is another reason you'd want to use the updated version of this app. You can test the SNR at different parts of the image and compare them directly. Anyway, what I want to do in general though is pick a part of the nebula or galaxy that isn't too bright or isn't too dim. Something that is dimmer but still clearly visible, like this part of Orion that I've selected. Right-click on Serial and get the statistics. Use either the median or the mean. Probably whichever one has a lower value just to be on the safe side. The mean looks lower and is 2115, so I'll go ahead and put that in the DSO plus SkyGlow box. Now I want to do the same thing, but in a place where there is no DSO signal and just the sky. Right-click and select Statistics again. Here I'd put in the median value, but generally I'd put in whatever is higher between the mean and the median to be a bit more in the estimate. Once that is done, a plot will appear that shows how SNR changes as you increase the number of subframes. You can use your mouse to hover over the line and it will give you the number of subs, the SNR, and the filter label. Pretty nice. Underneath is a table that gives the relevant information for how many subframes and total integration time you'll need to get a desired SNR. Major update here is that you can now enter multiple values from different subframes to compare things. But why would you want to do this? Well, here is a non-exhaustive list. You can see how much integration time you need for several filters at once, test the SNR of different subframes taken at different times to see how SNR changes over the course of an imaging session, get actual SNR results for different sub-exposure lengths, and more. I think seeing everything all at once is really useful. You know, this app took a little bit of thinking through. If you like this content, you might consider subscribing. I'd appreciate it. And if you'd like to support the channel even more, you can help keep this channel independent by becoming a member at Buy Me a Coffee. I appreciate all my members as well as new YouTube members. A big shout out to them for helping make this content possible. Now let me go ahead and find the DSO plus SkyGlow and SkyGlow values for O3. The dark and bias signals are the same because I'm using the same camera at the same gain settings. O3 subs were also taken at 300 seconds, so I just need to input 3 values for 3 boxes with the new information. How do I input the new values? Well, just add a comma and a space and then add them. That's why commas can't be used as filter label names. For O3, the SkyGlow plus background value is 2224. The sky glow background is 2167, and I'll add the label filter 03. Once we've done that, another line pops up for 03. Keep in mind that the colors of the lines change sort of randomly with each new filter that you put into it. So HA is not always going to be orange, 03 is not always going to be green, but they are here, which is kind of nice. Below, the table adds another row for the new filter. To get 60 SNR for 03, we need almost 32 hours of data. 03 has a much weaker signal to noise ratio, so maybe I don't want 60 SNR for 03, maybe 30 is better. But can the app deal with 2 SNR values? Yes, just add a comma and put 30. Commas separate the values for each filter. It's easy. Well, kind of. It is extremely important that each box should have either one value in it or the same number of values as the filter label box. If a box has one value in it, that value will be used in all the calculations. And that's fine if and only if the values are the same across all filters. So if your bias signal is the same across all filters, which it should be if you're using the same camera, you don't need to input the same value multiple times. But if you have 3 filters and 2 of them have the same bias value because one of the filters was taken with a different camera setting, then you will need to put all the bias values in there, even the ones that repeat. For example, let's say that for S2 my lights were taken at a different gain than HA and 03, the bias might be different. So I need to put the bias for all 3 filters in the app, even though HA and 03 have the same value. In fact, if I used a different gain setting, I'd also have to change the read noise and gain settings too. Alright, now let me do S2. Nice. You can see that I have 3 desired SNR values to match the 3 filters. I could just have one number, and it would calculate how many subs I need to get that SNR, or I could have 3 SNR values associated with each filter like I have here. Below the top plot and table, there is another plot and table. The app can give a theoretical estimate for how much integration time will change if you increase or decrease the sub exposure length. Theoretically, if you've swamped the read noise, then exposure time shouldn't matter much, but you can get the same calculations for subframes that are from 5 times shorter than the actual sub to 10 times longer. I'm not exactly sure how much I trust the estimate though. More experimentation is needed to see if it actually matches up in real life. So let's troubleshoot some problems a bit. What happens if your estimates are really similar and you can't see differences between the different filters on the plot? Well, click on the zoom icon at the top right of the graph and select part of the image to zoom in on. You can now see the differences between the lines. To zoom back out, you can click on the auto scale button to fit the graph nicely in the frame, or the home button to reset the axes to how they were originally. Now what happens if you're on a big project and have 7 filters calculated, but you just want to focus on the one filter for a bit on the plot? You can find the legend on the right side of the plot and click to toggle a line off or on. So I can click all of these filters except HA to turn them off. I can click them again to turn them back on. This doesn't affect the table, by the way. Now what happens if one of your filters shows NA? Well, first double check that you've input all your values correctly. Then make sure your DSO plus sky glow signal for that filter is greater than the sky glow background for the same filter. Here they're both 2574. It seems that part of the nebula I selected for the B filter has no signal, or its signal is so faint that it is the same as the background. Try choosing a different part of the DSO to get an estimate that is above the sky glow background. If your DSO plus sky glow is greater than the sky glow itself, then you probably just need more than 100,000 subs to get the desired SNR. The table only calculates up to 100,000 subframes. Try lowering the SNR for that filter or refer to the plot to see what you can expect for your SNR. It can tell you the SNR for up to 10,000 subframes, and you can use the max exposures to plot slider. The plot can tell you the individual SNR values rather than just how long you need to image to get a specific SNR like the table does. So how can you use the app? Well, go to deepskydetail.shinyapps.io/calculateSNR. It's free. I'll leave a link in the description, If you like this video on how to plan SNR, you'll probably love this one on why light pollution decimates SNR. It also exposes some misinformation about light pollution. Thanks for watching.